Welcome to Sleepy Science Student, where we explore the wonders of our planet one gentle drift at a time. Tonight, we're embarking on a slow, peaceful journey deep beneath our feet, into the very foundations that shape the world we call home. Tonight, we're going on a quiet, soothing journey into the remarkable world of plate tectonics, the elegant dance of continents across Earth's surface. We'll discover how our planet breathes and moves, reshapes itself over millions of years, and creates the mountains, valleys, and oceans that define our world. It's a story written in stone, whispered through earthquakes, and painted in the slow waltz of landmasses drifting across the globe. I hope this video isn't too interesting. Though, if it does happen to keep you awake, at least you'll be learning something fascinating about the dynamic crust beneath your feet. And if you find yourself pondering the movement of continents as you drift towards sleep, well, that's not the worst way to spend a peaceful night. Not the worst way at all. Before we begin our gentle exploration of Earth's restless surface, I'd love it if you gave this video a like and maybe even subscribed if you haven't already. It really helps this quiet little channel grow, reaching more curious minds who find comfort in learning about the slow, patient processes that shape our world. I'd also love to know where you're watching from and what time it is for you right now. Are you tuning in from a cozy bed in Santiago at midnight, lying atop the South American plate as it slowly inches westward? Or perhaps you're listening from a couch in Tokyo at noon, resting on the Pacific plate while it quietly subducts beneath Japan. Let me know in the comments. It's always such a joy to see our peaceful community scattered gently across the globe, each of you resting on your own piece of Earth's restless puzzle. Now, settle in. Get comfortable. You don't need to remember any of this. You don't need to take notes or stay alert. Just let the words wash over you like gentle waves lapping at a shore, slowly shaped by the patient work of tectonic forces over countless millennia. Let your shoulders relax. Slow down your breathing. And as we begin this gentle voyage into the heart of our dynamic planet, remember that the ground beneath you, though it feels solid and still, is part of an ancient, elegant dance that began billions of years ago and continues this very moment, imperceptibly slow, yet relentlessly powerful. This video is for educational and relaxation purposes only. It's not intended as medical advice, geological consulting services, or a guarantee that you won't wake up on a slightly different continent tomorrow morning, though at current plate movement rates, I promise you won't notice. Ready? Let's begin. Let's start our journey where all great geological stories begin, with what lies beneath. To understand how continents move, we first need to understand what our planet is made of, layer by gentle layer, like a cosmic onion wrapped in stone and time. Earth is not a solid ball of rock, though it might feel that way beneath your feet right now. Instead, our planet is structured in distinct layers, each with its own personality, its own characteristics, its own role to play in the grand theatre of planetary geology. Imagine, if you will, a soft-boiled egg. The shell is thin and brittle, the white is thick and viscous, and at the centre, the yolk is dense and hot. Earth, in its own way, follows a similar pattern, though on a scale that's almost impossible to truly comprehend. The outermost layer, the one you're resting on right now, is called the crust. It's surprisingly thin, a mere skin on the surface of our massive planet. Continental crust, the kind that forms the landmasses where most of us live, averages about 30 to 50 kilometers thick. That might sound substantial, but when you consider that Earth's radius is roughly 6,371 kilometers, the crust is proportionally thinner than the skin of an apple. Remarkably thin, delicately thin. Yet this fragile shell is where all of human history has unfolded, where every mountain you've climbed and every valley you've explored exists. Beneath the continents, the crust is mostly made of granite and similar rocks, light-colored, relatively low-density materials that geologists describe as felsic. This word comes from feldspar and silica, two of the main components of continental crust. These rocks are ancient, some dating back billions of years, preserving in their crystalline structure the memory of Earth's earliest days. They've been recycled, melted, reformed, and pushed up from below countless times, yet they remain stubborn and enduring. Oceanic crust, on the other hand, is quite different. Thinner, only about 5 to 10 kilometers thick, and denser, made primarily of basalt, a dark volcanic rock that forms when magma cools relatively quickly at the ocean floor. This basaltic rock is described as mafic, rich in magnesium and iron, which makes it heavier than its continental cousin. Because of this density difference, oceanic crust tends to sink beneath continental crust when the two meet, a process that will become wonderfully important as our story unfolds. But we're getting ahead of ourselves, slowly, gently. Now, let's pause for a moment and take a breath. Imagine you're descending through the crust, through layers of sedimentary rocks, past fossils and ancient seabeds, down through granite and basalt, deeper and deeper, until you reach the boundary where the crust ends and something else begins. This boundary is called the Mohorovičić discontinuity, or more affectionately, the MOHO. It's named after Croatian seismologist Andrija Mohorovičić, who discovered it in 1909 by studying how earthquake waves change speed at a certain depth. The MOHO marks a fundamental transition from the rigid crust to something stranger. Beneath the MOHO lies the mantle, and this is where things get fascinating in a particularly drowsy sort of way. The mantle makes up about 84% of Earth's volume. It extends from the base of the crust all the way down to about 2,900 kilometers deep. That's almost halfway to Earth's center. The mantle is composed of silicate rocks rich in iron and magnesium, rocks that under normal surface conditions would be solid. But here's where it gets interesting. Despite being solid rock, the mantle can flow. Very, very slowly. You might think this sounds impossible. How can solid rock flow? It's a bit like honey on a cold winter morning. If you try to pour it quickly, it seems solid, even rigid. But given enough time, given enough patience, it will flow, spreading slowly across your toast. The mantle behaves similarly, though on geological timescales. Under the immense heat and pressure deep within Earth, mantle rocks can undergo plastic deformation, flowing like an incredibly viscous fluid over thousands and millions of years. This property, being solid yet able to flow, is called plasticity, and it's absolutely essential to plate tectonics. The upper portion of the mantle, just below the crust, is cooler and more rigid than the deeper mantle. This rigid upper mantle, combined with the overlying crust, forms what geologists call the lithosphere. The lithosphere is broken into pieces, the famous tectonic plates that give plate tectonics its name. These plates are solid, coherent slabs that move around on top of something softer, something more yielding. That softer layer is called the asthenosphere, from the Greek word asthenes, meaning weak. But don't let the name fool you. The asthenosphere isn't weak in the sense of being fragile. Rather, it's weak in the sense of being ductile, pliable, able to flow. It extends from about 80 to 200 kilometers depth, though the exact boundaries are somewhat fuzzy, somewhat uncertain. The asthenosphere is hot enough that the rock there is partially molten in places, making it especially good at flowing, at deforming, at allowing the rigid plates above to glide along like ships on a very, very slow-moving sea. Now we continue our descent past the upper mantle, past the asthenosphere, into the lower mantle. Here the pressures are so immense that the rock, despite being hotter than the upper mantle, is actually more rigid. The lower mantle extends from about 660 kilometers down to the core mantle boundary at 2,900 kilometers. It's a realm of extreme conditions, temperatures reaching perhaps 3,700 degrees Celsius, pressures millions of times greater than at the surface. Yet the rock here is relatively static, moving only in slow convective currents that take millions of years to complete a single cycle. Speaking of which, let's talk briefly about convection. You're probably familiar with convection from everyday life. Boiling water, for instance. Hot water rises, cools at the surface, then sinks back down, creating a circulation pattern. The mantle does something similar, though far more slowly. Hot material from deep in the mantle gradually rises toward the surface, where it cools, becomes denser, and eventually sinks back down. This mantle convection is one of the driving forces behind plate tectonics, though the exact mechanisms are still being debated by scientists. Some believe plumes of hot material rise from deep in the mantle like lava lamps. Others think the convection is more passive, driven by the cooling and sinking of cold material at subduction zones. Perhaps it's both. Perhaps it's neither. The Earth keeps some secrets close. Deeper still, we reach Earth's core. The core is divided into two parts, the outer core and the inner core. The outer core, extending from about 2,900 to 5,150 kilometers depth, is liquid. A churning sea of molten iron and nickel, heated to temperatures around 4,000 to 5,000 degrees Celsius. This liquid metal flows in complex patterns, driven by Earth's rotation and by convection, and in doing so generates our planet's magnetic field, that protective magnetic bubble that shields us from solar wind and cosmic radiation. It's born in this hellish liquid forge deep below. Remarkable, really. At the very center of our planet, from 5,150 kilometers down to the center at 6,371 kilometers, lies the inner core. Despite temperatures exceeding 5,000 degrees Celsius, hotter than the surface of the sun, the inner core is solid. The pressure here is so extreme, so overwhelming, that iron and nickel are compressed into a solid crystalline sphere, roughly the size of the moon. It's growing slowly, very slowly, as the outer core cools and solidifies onto it, perhaps at a rate of 1 millimeter per year. In a few billion years, the outer core might be entirely solid, and Earth's magnetic field might cease. But that's a worry for another epoch, another eon. For now, the core spins quietly beneath us, a sphere of metal suspended in metal at the heart of our dynamic world. So there you have it, Earth's internal structure, from the thin crust we inhabit to the solid inner core at the center. Each layer plays its part in the grand dance of plate tectonics. The crust provides the stage, the lithosphere forms the dancers, the plates themselves. The asthenosphere is the floor they glide upon, and the convecting mantle beneath provides the music, the energy that keeps everything moving, slowly but inexorably across geological time. Take a moment to picture this. Imagine all those layers stacked beneath you, each one contributing to the subtle, imperceptible motion of the ground you're resting on. You're lying on a plate of lithosphere, floating on the asthenosphere, above a mantle slowly churning with heat from the core below. It's quite a thought, isn't it? And yet it all happens so gently, so quietly, that you'll never feel it in a human lifetime. The continents drift at about the same rate your fingernails grow, a few centimeters per year at most. Patient, persistent, eternal in its slow progression. For most of human history, people assume the continents were fixed in place, immovable as the ground itself seemed to be. Mountains were eternal. Oceans were permanent. The map of the world was seen as something drawn by divine hands at the moment of creation, unchanging and unchangeable. But then along came curious minds, asking questions, noticing patterns, wondering about the remarkable fit between coastlines on opposite sides of the Atlantic Ocean. One of those curious minds belonged to Alfred Wegener, a German meteorologist and polar researcher with wild ideas and gentle persistence. In the early 20th century, Wegener proposed something radical, something that would eventually revolutionize geology, but was initially met with skepticism, even ridicule. He suggested that the continents were not fixed, but rather had once been joined together in a single supercontinent, which he called Pangaea, from the Greek words pan, meaning all, and Gaia, meaning earth. All earth. One massive landmass that later split apart and drifted to the positions we see today. Wegener first presented his theory in 1912, and he spent much of the rest of his life gathering evidence to support it. What evidence, you might wonder? Well, let's explore it together, slowly and thoroughly. First, there was the fit of the continents. Look at a map. Not a casual glance, but a long, contemplative study. Notice how the eastern coast of South America seems to nestle perfectly against the western coast of Africa, like two pieces of a jigsaw puzzle separated by an ocean. Wegener noticed this too, and he wasn't the first. Even in the late 1500s, cartographers had remarked on the similarity. But Wegener did more than notice. He measured, he calculated, and he found that if you moved the continents together, matching not just the coastlines but the edges of the continental shelves, the underwater extensions of the continents, the fit was remarkably precise. But similar shapes alone wouldn't convince the scientific community. Coincidence, they said. So Wegener gathered more evidence. He looked at fossils. Remarkably, he found identical fossil species on continents now separated by vast oceans. Take Mesosaurus, for example, a small freshwater reptile that lived about 300 million years ago. Its fossils are found in both Brazil and southern Africa. Now, Mesosaurus couldn't swim across the Atlantic. It lived in freshwater lakes and rivers. How, then, did it end up on two separate continents thousands of kilometers apart? The simplest explanation, Wegener argued, was that when Mesosaurus was alive, South America and Africa were connected. The creature didn't cross an ocean. It lived in a world where there was no ocean between those landmasses. There were other fossil matches too. Glossopteris, a fern-like plant, left its fossil remains in South America, Africa, India, Australia, and Antarctica, continents now scattered across the southern hemisphere. Cynognathus and Lystrosaurus, ancient reptiles, showed similar distribution patterns. These creatures and plants couldn't have crossed thousands of kilometers of open ocean. Yet there they were, their fossilized bones and leaves speaking quietly across millions of years, telling a story of connected landmasses, of ancient continuity now broken. Wegener also examined rock formations and mountain belts. He found that geological structures in eastern South America matched those in western Africa. Ancient mountain ranges, formed hundreds of millions of years ago, seemed to line up when you place the continents together. The Appalachian Mountains in North America appeared to be a continuation of the Caledonian Mountains in Scotland and Scandinavia. These weren't just similar rock types scattered randomly. They were continuous geological features, now separated by an ocean, but clearly part of the same ancient system. It was as if someone had torn a page of geological history down the middle and then tried to claim the two halves had always been separate. Then there was the evidence from ancient climates, preserved in the rocks themselves. Wegener found glacial deposits, rocks and sediments left behind by ancient ice sheets, in places that are now tropical or temperate. Parts of Africa, India, South America, and Australia all showed signs of glaciation around 300 million years ago. Now, glaciers form in cold climates, typically near the poles. Why would these now scattered continents have been glaciated at the same time? Wegener proposed that they were all part of a southern supercontinent called Gondwana, positioned over the South Pole. As this supercontinent broke apart and the pieces drifted to their current positions, they carried with them the frozen signatures of their polar past. You might think this evidence was compelling, and it was. But there was a problem, a significant one. Wegener couldn't explain how the continents moved. He proposed several mechanisms: tidal forces from the moon and sun, centrifugal force from Earth's rotation, something he called flight from the poles. But none of these forces were strong enough to push continents through solid ocean crust. Geologists and physicists calculated the forces involved and found Wegener's mechanisms woefully inadequate. Without a convincing explanation for how continents could plow through the ocean floor like ships through ice, the scientific establishment largely rejected his theory. Continental drift was seen as an interesting idea, but ultimately unworkable. Wegener was dismissed by many as a dreamer, an outsider meddling in geology without proper credentials. Alfred Wegener died in 1930 during an expedition to Greenland, his theory largely unaccepted. He never lived to see the vindication that would come decades later. It's a melancholy thought, isn't it? A person dedicating their life to an idea, gathering evidence, facing skepticism, and passing away before the world acknowledged they were right. But science, like plate tectonics itself, moves slowly. Ideas drift, collide, subduct, and re-emerge transformed. Wegener planted a seed, and though he didn't see the tree grow, his ideas would eventually blossom into one of the most important theories in Earth science. Let's pause here and reflect. The story of continental drift is not just about rocks and fossils. It's about human curiosity, about pattern recognition, about having the courage to propose something radically different from accepted wisdom. Wegener looked at the world and saw not permanence, but change. Not fixity, but motion. He imagined continents as wanderers, slow travelers across the face of the earth. And though he couldn't explain the mechanism, he trusted the evidence, trusted the patterns he observed. In a way, his story is about patience, waiting for understanding to catch up with observation, waiting for technology and new discoveries to reveal the missing pieces of the puzzle. And those missing pieces would come, quietly, methodically, in the decades following Wegener's death. During World War II and the Cold War era that followed, there was a massive expansion in oceanography, driven partly by military interests in submarine warfare and undersea surveillance. Scientists began to map the ocean floor in unprecedented detail, using sonar and other technologies. And what they discovered was astonishing, transformative, and perfectly conducive to a sleepy contemplation of Earth's hidden architecture. They found that the ocean floor was not flat and featureless as many had assumed. Instead, it was a landscape of mountains and valleys, ridges and trenches. Most remarkably, they discovered a continuous mountain chain running through the center of the Atlantic Ocean, the Mid-Atlantic Ridge. This underwater mountain range, rising kilometers above the surrounding abyssal plains, stretches from the Arctic to the Antarctic, and it wasn't unique. Similar ridges were found in other oceans, the East Pacific Rise, the Mid-Indian Ridge. Together, these features formed a connected system of mid-ocean ridges encircling the globe like the seams on a baseball, gently curved, elegantly continuous, quietly mysterious. But the most crucial discovery came from studying the magnetism of rocks on the ocean floor. As you might know, Earth's magnetic field periodically reverses. The north and south magnetic poles switch places. These reversals are recorded in rocks as they form, like a paleomagnetic tape recording of Earth's magnetic history. When scientists measured the magnetic properties of rocks on either side of mid-ocean ridges, they found something extraordinary. Symmetrical patterns of magnetic stripes, mirroring each other on opposite sides of the ridge. Rocks near the ridge were magnetized in one direction. Moving away from the ridge, the rocks switched to the opposite polarity, then switched back, then switched again. The pattern was symmetrical, orderly, and completely unexpected. This pattern could only make sense if new ocean floor was being created at the ridges and then spreading outward, carrying with it the magnetic signature of the time it formed. This process, called seafloor spreading, was proposed independently by Harry Hess and Robert Dietz in the early 1960s. It provided the mechanism that Wegener had lacked. Continents weren't ploughing through ocean crust. Instead, new crust was being created at mid-ocean ridges, pushing the older crust, and the continents embedded in it, apart. The continents were passengers on moving plates of lithosphere, not ships forcing their way through a static sea. With seafloor spreading, continental drift was reborn as plate tectonics, a comprehensive theory explaining not just the movement of continents, but the entire dynamic system of Earth's lithosphere. The plates move, new crust forms at ridges, old crust descends back into the mantle at deep ocean trenches. Earthquakes and volcanoes mark the boundaries between plates. Everything fit together, elegantly, inevitably, like pieces of a puzzle that had been waiting for someone to see the picture. By the late 1960s and early 1970s, plate tectonics had achieved widespread acceptance in the geological community. It became the unifying theory of geology, much as evolution is the unifying theory of biology. Suddenly, phenomena that had seemed unrelated, earthquakes, volcanoes, mountain building, ocean trenches, were all part of one grand system. The Earth was no longer static but dynamic, constantly reshaping itself through the slow, patient work of moving plates. So Wegener was vindicated, though he never knew it. His continental drift became plate tectonics. His observation became theory, became fact. And now we understand that the map of Earth has never been static. It's a snapshot, a momentary configuration in an endless dance of drifting landmasses. The world looked different in the past. It will look different in the future, and that's deeply, quietly beautiful. Take a breath, let that sink in. The ground beneath you is part of a story billions of years in the telling, and the chapter we're living through is just one of countless many. Now that we understand that Earth's lithosphere is broken into moving plates, let's explore what happens where those plates meet. These boundaries between plates are where the most dramatic and important geological activity occurs. Mountains rise, earthquakes shake the ground, volcanoes erupt. But even these dramatic events unfold slowly, gently, over the vast canvas of geological time. And at a comfortable distance, from the warmth of your bed, they become not terrifying, but fascinating, worthy of drowsy contemplation. There are three main types of plate boundaries, each defined by how the plates move relative to one another. First, there are divergent boundaries, where plates move apart. Second, there are convergent boundaries, where plates move toward each other. And third, there are transform boundaries, where plates slide horizontally past one another. Each type creates its own characteristic geological features, its own patterns of seismic activity, its own contributions to the ever-changing face of our planet. Let's begin with divergent boundaries, where plates separate, creating space between them. The most prominent examples of divergent boundaries are the mid-ocean ridges we mentioned earlier, the Mid-Atlantic Ridge, the East Pacific Rise, and others. At these underwater mountain ranges, magma wells up from the mantle below, filling the gap created as the plates pull apart. This magma cools and solidifies, forming new oceanic crust. It's a bit like a conveyor belt running in reverse at both ends, constantly producing new seafloor that spreads outward from the ridge. The process is remarkably orderly. As the plates separate at rates of a few centimeters per year, about as fast as your hair grows or grass lengthens in summer, magma rises through cracks in the lithosphere. This molten rock, heated to over 1,000 degrees Celsius, encounters the cold seawater and cools rapidly, forming pillow-shaped structures of basalt. These pillow lavas accumulate at the ridge axis, building up the underwater mountain. Meanwhile, the newly formed crust on either side of the ridge gradually moves away, making room for more magma to rise and solidify. It's a continuous process, patient and persistent, creating ocean floor that didn't exist before. You might wonder where all this new crust comes from. After all, Earth isn't expanding. If new ocean floor is constantly being created at mid-ocean ridges, what happens to the old ocean floor? This is where the second type of plate boundary comes in, convergent boundaries, where plates move toward each other. And this is where things get particularly interesting, in a gentle geological sort of way. At convergent boundaries, two plates collide, but the outcome depends on what type of crust is involved. Remember that oceanic crust is denser than continental crust. It's made of heavy basalt rather than lighter granite. When an oceanic plate meets a continental plate, the denser oceanic plate slides beneath the continental plate in a process called subduction. The oceanic plate is forced down into the mantle, where it's heated, partially melted, and eventually recycled back into Earth's interior. This descending slab creates a deep ocean trench, some of the deepest places on Earth. The deepest of these trenches is the Mariana Trench in the Western Pacific. where the Pacific Plate subducts beneath the small Mariana Plate. At its deepest point, called Challenger Deep, the ocean floor plunges nearly 11 kilometers below sea level. If you placed Mount Everest, the tallest mountain above sea level, into the Mariana Trench, its peak would still be more than 2 kilometers underwater. It's a profound depth, a realm of crushing pressure and absolute darkness, where strange creatures have adapted to conditions that would instantly kill most life forms, and it's all created by the slow, inexorable descent of a tectonic plate into the mantle. Subduction zones are incredibly important to plate tectonics. They're where old ocean crust is destroyed, balancing the creation of new crust at mid-ocean ridges. They're also where some of the most powerful earthquakes occur, as the descending plate grinds against the overriding plate, building up stress that's periodically released in violent shaking. And they're where many of the world's volcanoes form, as water and other volatiles from the subducting plate lower the melting point of the mantle above, creating magma that rises through the overlying crust to erupt at the surface. Think of the Ring of Fire, the horseshoe-shaped belt of volcanoes and earthquake zones that encircles the Pacific Ocean. This ring marks the boundaries of the Pacific Plate as it subducts beneath surrounding plates. Japan, the Philippines, Indonesia, the west coast of South and North America, all are part of this fiery ring, all marked by frequent earthquakes and active volcanoes. Yet for all the drama, for all the potential for catastrophe, these processes unfold with a strange kind of patience. Years, decades, even centuries can pass between major earthquakes. Volcanoes may sleep for generations before awakening. The plates move at their leisurely pace, unconcerned with human timescales, operating on the deep time of geology. Now, what happens when two oceanic plates converge? In this case, the older, denser plate typically subducts beneath the younger one. The result is similar to oceanic continental convergence. A deep trench forms, and volcanic activity occurs above the subduction zone. But instead of volcanoes forming on a continent, they form as a chain of volcanic islands called an island arc. The Aleutian Islands, stretching west from Alaska, are an example. So are the islands of Japan, the Philippines, and many others in the Western Pacific. These volcanic arcs are windows into Earth's interior, places where the mantle's heat and energy manifest at the surface in spectacular displays of molten rock and ash. The third type of convergence occurs when two continental plates collide. Here, neither plate subducts. Continental crust is too light, too buoyant to be forced down into the mantle. Instead, the crust crumples, folds, and thrusts upward, building massive mountain ranges. The Himalayas, the tallest mountains on Earth, are the result of the Indian plate colliding with the Eurasian plate. This collision began about 50 million years ago and continues today, with the Indian plate still pushing northward at a rate of about 5 centimeters per year. Mount Everest is still growing, gaining a few millimeters in height each year, as the ancient collision that birthed it continues its slow, relentless work. Continental collisions like this create not only mountains but also deep-seated changes in the crust itself. Rock, layers that once lay horizontally, are folded into complex patterns. Rocks from deep in the crust are thrust upward and exposed at the surface. Metamorphic processes, driven by heat and pressure, transform one type of rock into another. The result is some of the most geologically complex and spectacular terrain on Earth, a testament to the power of slow, patient forces acting over immense periods of time. Take a breath. Imagine the Himalayas, that roof of the world, still rising, still being built, grain by grain, year by year, even as you lie here listening to these words. Now let's turn to the third major type of plate boundary: transform boundaries. At these boundaries, plates slide horizontally past each other, neither creating nor destroying crust. The most famous example is the San Andreas Fault in California, where the Pacific plate slides northwestward past the North American plate. This motion is not smooth. The plates are locked together by friction, and stress builds up over decades or centuries. Eventually, the stress overcomes the friction, and the plates suddenly slip, releasing energy in an earthquake. Then the process begins again. Lock, stress, slip, repeat. It's a cycle measured in decades and centuries, invisible to human perception in its slow build-up, but occasionally terrifyingly sudden in its release. Transform boundaries are relatively common in the ocean, where they offset segments of mid-ocean ridges. These oceanic transform faults can be hundreds of kilometers long, cutting across the seafloor in straight lines that mark the boundary between two plates sliding past each other. Earthquakes occur along these faults, but because they're far from land, they rarely affect humans. They're quiet reminders of the restless nature of Earth's crust, hidden beneath thousands of meters of water, doing their work unseen and unfelt. So we have three types of boundaries: divergent, convergent, and transform. Together, they form a global network, a planetary system of motion and change. New crust forms at divergent boundaries. Old crust is destroyed at convergent boundaries. And at transform boundaries, plates simply slide past each other, neither creating nor destroying, just moving. It's an elegant system, beautifully balanced, with each type of boundary playing its essential role. If you were to look at a map showing all the plate boundaries on Earth, you'd see a fascinating pattern. The boundaries outline discrete plates, large coherent pieces of lithosphere. There are 7 major plates: the Pacific, North American, Eurasian, African, Antarctic, Indo-Australian, and South American. There are also numerous smaller plates: the Nazca, Philippine, Arabian, Caribbean, and others. Each plate is moving at its own speed and direction, driven by forces we'll explore later. And where the plates meet, that's where the geological action happens. That's where the Earth reveals its dynamic nature. It's worth noting that plate boundaries are not always simple lines. Sometimes they're zones, broad regions where deformation is distributed across multiple faults and structures. The boundary between the Indian and Eurasian plates, for example, isn't a single fault, but a vast region of crustal deformation extending across much of Central Asia. Earthquakes in this region can occur hundreds or even thousands of kilometers from the main collision zone. The Earth is complex, messy even, refusing to conform to neat, simple models. And that's part of what makes it endlessly fascinating, endlessly worthy of quiet, contemplative study. Let's pause again and take stock. We've covered a lot of ground, or rather, a lot of lithosphere. We've learned that plates can diverge, converge, or slide past each other. We've seen how these movements create mid-ocean ridges, deep trenches, volcanic island arcs, towering mountain ranges, and earthquake-prone faults. And underlying all of this is the simple, elegant principle that Earth's surface is not static but mobile, constantly rearranging itself through the slow dance of plate tectonics. The planet breathes, moves, reshapes, and we're fortunate enough to live on it during one brief moment in its long, storied existence. Now, let's dive deeper, quite literally, into the process of seafloor spreading. That elegant mechanism by which ocean basins are born, grow, and ultimately vanish back into the mantle. It's a cycle of creation and destruction, playing out over millions of years, invisible to us, except through the careful detective work of scientists studying rocks, magnetic patterns, and the topography of the seafloor. Imagine you're at a mid-ocean ridge, that underwater mountain range running through the center of ocean basins. The water here is deep, perhaps 2 or 3 kilometers above you, and cold, hovering just above freezing. Yet beneath the seafloor, molten rock waits, heated to over 1,000 degrees Celsius by the mantle below. The contrast is remarkable. A few meters separate, ice-cold seawater from molten basalt, with only thin oceanic crust between them. At the very center of the ridge, there's a rift valley, a deep crack where the two plates are pulling apart. This valley can be a kilometer or more deep and several kilometers wide. It's bounded by steep cliffs and dotted with volcanic features, cones, fissures, lava flows, frozen in mid-eruption. And all along this rift, magma seeps upward from below, filling the gap created by the separating plates. When this superheated magma encounters cold seawater, it cools rapidly, forming distinctive pillow-shaped structures. These pillow lavas get their name from their appearance, rounded, bulbous forms that look remarkably like cushions stacked on top of each other. Each pillow is a snapshot of a moment when molten rock met cold water and froze almost instantly, preserving the shape it had at that instant. Over time, countless pillow lavas accumulate, building up the seafloor, creating new oceanic crust molecule by molecule, crystal by crystal. But magma doesn't only erupt at the seafloor surface. Some solidifies in vertical cracks within the crust, forming structures called dikes. These dikes, sheets of once molten rock now frozen solid, stack one atop another in a sheeted dike complex. Below the dikes, magma chambers cool more slowly, crystallizing into coarse-grained rock called gabbro, and below that, the mantle rock from which the magma came. This layered structure, pillow lavas, sheeted dikes, gabbro, mantle rock, is called an ophiolite sequence, and it's the standard architecture of oceanic crust, formed at every mid-ocean ridge, repeated throughout all the ocean basins. As new crust forms at the ridge axis, the older crust on either side is pushed away, gradually moving toward distant subduction zones where it will eventually be consumed. This process is symmetrical. The crust on the western side of a mid-ocean ridge is a mirror image of the crust on the eastern side. The youngest rocks are at the ridge center. Moving away in either direction, the rocks get progressively older. It's a beautiful pattern, a natural timeline written in stone and magnetism, telling the story of ocean basin evolution. The Atlantic Ocean is currently spreading. The mid-Atlantic ridge runs down its center, creating new seafloor that pushes Europe and Africa away from the Americas at about 2 to 3 centimeters per year. This might not sound like much, but over millions of years, it adds up. 200 million years ago, there was no Atlantic Ocean. South America was snuggled up against Africa, North America against Europe. Then the supercontinent Pangaea began to break apart, and a rift opened, which became the Atlantic. That rift is still spreading today, and the Atlantic is still growing. One day, perhaps in another 200 million years, the process might reverse, and the Atlantic might close again, bringing the continents back together. But that's speculation, a gentle wondering about the far future. The Pacific Ocean, on the other hand, is shrinking. Unlike the Atlantic, which has a mid-ocean ridge but no major subduction zones consuming its edges, the Pacific is ringed by subduction zones. The Pacific Plate and surrounding smaller plates are being consumed at trenches around the Pacific's perimeter faster than new crust is being created at the East Pacific Rise and other ridges within the basin. Over geological time, the Pacific is closing, slowly, inevitably, like a great blue mouth gradually shutting. In another few 100 million years, the Pacific might be gone entirely, replaced by new mountain ranges where ocean once existed. It's a melancholy thought in a way, the largest ocean on Earth, vanishing, leaving only rocks and memories. But such is the nature of plate tectonics. Nothing is permanent. Everything flows, changes, becomes something else. Seafloor spreading also has fascinating implications for life on Earth. At mid-ocean ridges, particularly at hydrothermal vents, seawater seeps into cracks in the newly formed crust, gets heated by the magma below, and then erupts back into the ocean laden with dissolved minerals and chemicals. These hydrothermal vents support unique ecosystems, communities of organisms that don't depend on sunlight for energy, but instead derive their sustenance from chemicals in the vent fluids. Tube worms, clams, bacteria, and other creatures thrive in these extreme environments, clustered around black smokers and white smokers, those towering chimneys of mineral-rich water rising from the sea floor. Some scientists think that life on Earth might have originated at hydrothermal vents. The conditions there, chemical energy, heat, mineral-rich water, could have been conducive to the formation of the first organic molecules, the first primitive cells. If that's true, then seafloor spreading isn't just a geological process. It's a biological one as well, intimately tied to the origin and evolution of life itself. We are, in a sense, children of the mid-ocean ridges, descendants of organisms that first emerged in the darkness of the deep sea, where tectonic plates part and magma meets water. So seafloor spreading is both simple and profound. On one level, it's just magma filling a gap as plates separate. On another, it's the mechanism that drives continental drift, creates ocean basins, supports unique ecosystems, and might have given birth to life itself. It's a process that's been occurring for billions of years, that will continue for billions more, as long as Earth's interior remains hot and convecting. And lying here, contemplating this, you're connected to it, resting on a plate that's part of this grand system, moving imperceptibly, carrying you along on a journey you'll never feel, but that's happening nonetheless, reliably, patiently, eternally. Now we turn our attention to one of the most fascinating and geologically significant features of plate tectonics, subduction zones. These are the places where oceanic lithosphere, having traveled thousands of kilometers from its birthplace at a mid-ocean ridge, finally meets its end, descending back into the mantle from whence it came. It's a process of recycling, of renewal, of the Earth consuming its own surface and transforming it into something new. Take a breath. Let's descend together into these remarkable features. Subduction begins when two plates converge, and one, the denser of the two, begins to sink beneath the other. Most commonly, this involves oceanic lithosphere sliding beneath either continental lithosphere or younger, more buoyant oceanic lithosphere. The process isn't instantaneous. It begins slowly, tentatively, as the edge of the denser plate starts to bend downward. Over millions of years, this bending creates a deep depression in the ocean floor, a trench, the deepest features on Earth's surface. These trenches are remarkable places. The Mariana Trench, which we mentioned earlier, reaches depths of nearly 11 kilometers. The Peru-Chile Trench off the west coast of South America, the Japan Trench off the coast of Japan, the Tonga Trench in the southwestern Pacific, all plunge to depths that dwarf our deepest mines and wells. To put it in perspective, if you could stand at the bottom of the Mariana Trench and look up, you'd be looking through more than 10 kilometers of water. The pressure there is over 1,000 times atmospheric pressure at sea level. It's crushing. Absolute. Darkness beyond darkness. And yet, remarkably, life exists even there. Strange fish with transparent heads, giant single-celled organisms, bacteria that have adapted to conditions that seem utterly hostile to life. The Earth is full of surprises, full of life persisting in the most unlikely places. But the trench is just the beginning of the subduction story. The real drama unfolds beneath the surface as the descending slab of lithosphere plunges into the mantle. This descent isn't smooth. The downgoing plate and the overriding plate are locked together by friction along their interface, a contact zone called the mega-thrust fault. Stress builds up along this fault as the plates try to move relative to each other but are held in place by friction. For decades, sometimes centuries, the stress accumulates. The rocks deform elastically, bending like a spring being compressed, and then, when the stress finally exceeds the friction holding the plates together, they slip suddenly and violently, releasing all that stored energy in a megathrust earthquake. These megathrust earthquakes are the largest, most powerful earthquakes on Earth. The 2011 Tohoku earthquake in Japan, which triggered a devastating tsunami, and the Fukushima nuclear disaster, was a magnitude 9.1 megathrust event. The 2004 Indian Ocean earthquake, which caused the catastrophic Boxing Day tsunami, was magnitude 9.1 to 9.3. The 1960 Valdivia earthquake in Chile, the most powerful earthquake ever recorded, reached magnitude 9.5. These are events that release energy equivalent to thousands or even tens of thousands of nuclear bombs. They can shift entire islands horizontally by meters. They can change Earth's rotation ever so slightly. They remind us, in the most dramatic way possible, that the ground beneath our feet is not as stable as it seems. But let's step back from the catastrophic and return to the slow, patient processes we've been contemplating. The descending slab doesn't just sink straight down. It typically descends at an angle, usually between 30 and 60 degrees, though this varies. As it descends, it undergoes profound changes. The increasing pressure and temperature transform the rocks of the oceanic crust, changing their mineralogy, their structure. Minerals that were stable at the surface become unstable at depth and transform into denser forms. This process of metamorphism continues as the slab descends, with different minerals forming at different depths. One particularly important aspect of subduction is what happens to the water that the slab carries down with it. Oceanic lithosphere, having spent millions of years on the seafloor, is saturated with seawater. This water is locked in minerals, in cracks and pores, in the very structure of the rocks themselves. As the slab descends and heats up, these water-bearing minerals become unstable. They release their water, which then rises into the overlying mantle wedge, the portion of the mantle caught between the subducting slab and the overriding plate. This water has a profound effect. It lowers the melting point of the mantle rock in the wedge, causing it to partially melt even though it hasn't gotten significantly hotter. It's a bit like adding salt to ice, which lowers its melting point and causes it to melt at temperatures below 0 Celsius. The water released from the subducting slab acts similarly on the mantle, inducing melting and generating magma. This magma, being less dense than the surrounding solid rock, rises buoyantly through the overlying plate. If the overlying plate is oceanic, the magma may erupt to form a volcanic island arc. If it's continental, it rises through the continental crust and erupts to form a volcanic arc on land. The volcanoes formed above subduction zones have a characteristic style of eruption. Unlike the relatively gentle, effusive eruptions typical of mid-ocean ridges or hotspots like Hawaii, subduction zone volcanoes tend to erupt explosively. The magma here is richer in silica, more viscous, and contains more dissolved gases. When this magma reaches the surface, the sudden decrease in pressure causes the gases to expand explosively, fragmenting the magma into ash and pumice that can be blasted kilometers into the atmosphere. These explosive eruptions can be devastating. Think of Mount Vesuvius burying Pompeii or Mount Pinatubo in 1991, ejecting so much ash and sulfur dioxide that it temporarily cooled the entire planet. Yet, for all their power, even these volcanoes operate on the slow timescales of geology. A volcano might erupt violently for days or weeks, then sleep for decades, centuries, or even millennia before awakening again. Between eruptions, the only sign of activity might be a plume of steam or gases, or perhaps small earthquakes deep beneath the mountain as magma slowly accumulates in chambers below. The violence, when it comes, is fleeting. The patient, slow processes are the norm. And this, perhaps, is what makes them so soothing to contemplate from a safe distance, knowing that even the most dramatic geological events are brief interruptions in the long, slow rhythm of planetary processes. As the subducting slab continues its descent, it eventually reaches depths where even the minerals formed by earlier metamorphism become unstable. At around 660 kilometers depth, there's a major transition in the mantle's structure, a boundary where minerals undergo a phase change to even denser forms. For a long time, scientists debated whether subducting slabs could penetrate this boundary, or whether they would stall there, unable to push through. Modern seismic imaging has resolved this debate, at least partially. Some slabs do appear to penetrate into the lower mantle, descending all the way to the core mantle boundary, nearly 3,000 kilometers down. Others seem to flatten out and spread horizontally, at the 660-kilometer discontinuity, at least temporarily. The behavior varies depending on the age, temperature, and composition of the slab, and on the mantle conditions it encounters. Think about this for a moment. A piece of ocean floor, formed perhaps 200 million years ago at a mid-ocean ridge, travels across an ocean basin, collides with a continent or another oceanic plate, and begins its descent. It sinks through the mantle over millions of years, undergoing metamorphism, releasing water, generating magma, triggering earthquakes. Eventually, perhaps 100 million years after it began its descent, it reaches the core mantle boundary, where it might pile up with other subducted material in a graveyard of ancient seafloor. Or perhaps it's incorporated into rising mantle plumes that will eventually bring it back toward the surface. Either way, it's a journey of hundreds of millions of years, covering thousands of kilometers, transforming a piece of the Earth's surface into something unrecognizable, recycling it back into the planetary interior. This recycling is essential to plate tectonics. Without subduction, new ocean floor would continue forming at mid-ocean ridges with nowhere to go. The ocean basins would fill in, continents would spread ever farther apart, and eventually the system would grind to a halt. But with subduction, there's a balance. New crust forms at ridges. Old crust descends at trenches. The total amount of lithosphere remains roughly constant, while its configuration constantly changes. It's an elegant system, self-regulating, sustainable over billions of years. Subduction also plays a crucial role in the chemical evolution of Earth. Elements that were once at the surface, carbon, nitrogen, water, various minerals, are carried down into the mantle by subducting slabs. Some of these materials are returned to the surface through volcanic eruptions above subduction zones. Others are sequestered in the deep mantle, perhaps for hundreds of millions of years, before being brought back to the surface by mantle plumes or other processes. This deep cycling of elements between the surface and the interior is essential to maintaining Earth's habitability, regulating the composition of the atmosphere and oceans over geological time. So subduction zones are not just destructive features where crust is consumed. They're recycling centers, chemical processing plants, the driving force behind some of Earth's most spectacular geological features. They're where old makes way for new, where surface meets interior, where the planet renews itself, and they operate with a patience, a persistence that's humbling to contemplate. The next time you hear about an earthquake in Japan or a volcanic eruption in Indonesia, remember, you're witnessing a manifestation of subduction, a process that's been shaping our planet for billions of years and will continue for billions more. Rest easy in that continuity, that ancient rhythm. Let's shift our focus now to the third type of plate boundary, transform faults, where plates slide horizontally past each other. These are perhaps the most enigmatic of plate boundaries, neither creating nor destroying crust, simply accommodating the relative motion of plates. They're like the joints in a tiled floor, allowing movement without breaking the tiles themselves, quiet most of the time, sudden and dramatic when they do move, worthy of our gentle attention. The most famous transform fault is undoubtedly the San Andreas Fault in California. This feature runs roughly north-south through California for about 200 kilometers, from the Salton Sea in the south to Cape Mendocino in the north. It marks the boundary between the Pacific Plate to the west and the North American Plate to the east. The Pacific Plate is moving northwestward, relative to North America, at about 50 millimeters per year, roughly the rate at which your fingernails grow. In human terms, this is slow, imperceptible, but over millions of years, it adds up to hundreds of kilometers of displacement. Imagine, if you will, standing astride the San Andreas Fault, 1 foot on the Pacific Plate, 1 on the North American Plate. If you could live long enough, you'd notice your feet slowly separating horizontally. Over 1 million years, they'd be 50 kilometers apart. Over 10 million years, 500 kilometers. The city of Los Angeles, which sits on the Pacific plate, is gradually moving northwest relative to San Francisco, which is on the North American plate. In about 15 million years, Los Angeles will be adjacent to San Francisco. And in perhaps 50 million years, Los Angeles will have slid past San Francisco entirely and be heading toward Alaska. It's a curious thought, isn't it? Cities moving relative to each other, not because people are moving them, but because the ground they're built on is part of separate plates drifting in different directions. But of course, this motion isn't smooth. The two plates aren't sliding past each other continuously, like ice on ice. Instead, they're locked together by friction along most of the fault, with stress slowly building up as the plates try to move. This is called the elastic rebound theory, proposed by geologist Harry Fielding Reid after studying the 1906 San Francisco earthquake. Reid recognized that the crust on either side of the fault was being elastically deformed, bent, and stressed as the plates tried to move but were held in place. Eventually, the stress exceeded the strength of the rock, the fault ruptured, and the two sides suddenly slipped past each other, releasing the stored elastic energy as seismic waves that shook the ground violently. That 1906 earthquake was a magnitude 7.9 event, one of the most destructive earthquakes in US history. The ground ruptured along about 480 kilometers of the San Andreas Fault, with horizontal displacements of up to 6 meters in some places. San Francisco was devastated, not just by the shaking, but by the fires that broke out afterward, fed by broken gas lines and difficult to fight with broken water mains. Over 3,000 people died. It was a stark reminder that the apparently solid ground could betray us, could suddenly move in ways that brought down buildings and shattered lives. Yet for all its drama, the 1906 earthquake was just one moment in the long history of the San Andreas Fault. Before it, there were other great earthquakes. After it, there have been and will be more. The fault has been active for millions of years and will remain active for millions more. Each earthquake is a brief punctuation mark in a long sentence of slow, steady motion. The periods between earthquakes are far longer than the earthquakes themselves. Most of the time, the fault is quiet, locked, with stress slowly accumulating. The earthquake, when it comes, is almost a relief, a sudden release of tension, allowing the process to begin again. Transform faults aren't unique to California or even to continental settings. In fact, they're far more common in the ocean, where they offset segments of mid-ocean ridges. Picture this. A mid-ocean ridge doesn't run in a perfectly straight line. Instead, it's made up of short segments offset from each other. Between these segments, transform faults connect the offset ridge portions, accommodating the differential spreading rates and directions. These oceanic transform faults can be hundreds of kilometers long, cutting across the seafloor in remarkably straight lines. The seafloor on either side of an oceanic transform fault is different in age. On one side, you might have seafloor that formed recently at a ridge segment. On the other side, seafloor that's millions of years older. This creates an interesting situation. The two sides of the fault are at different elevations, with the older, cooler seafloor sitting lower than the younger, warmer seafloor. The result is a subtle topographic step, a change in depth that marks the fault even though it might not be obvious in other ways. Earthquakes occur along these faults too, though being far from land and typically not large enough to generate tsunamis, they rarely affect humans. They're reminders of the constant motion, the endless adjustments happening beneath the sea. One fascinating aspect of transform faults is that they're conservative boundaries. Unlike divergent boundaries, which create new crust, or convergent boundaries, which destroy it, transform boundaries neither create nor destroy. They simply accommodate horizontal motion. This means that the total length of all plate boundaries must balance. For every meter of new crust created at a mid-ocean ridge, a meter must be destroyed at a subduction zone or accommodated by lateral motion at a transform fault. It's a global bookkeeping system, ensuring that Earth neither grows nor shrinks as plates move around on its surface. Transform faults also provide geologists with remarkable opportunities to study Earth's crust. Because they involve horizontal displacement, they can bring rocks from deep in the crust up to the surface, exposing layers that would otherwise be hidden kilometers below. The San Andreas Fault, for instance, has exhumed rocks from various depths, allowing geologists to study the structure and composition of the crust without having to drill deep wells. It's like the Earth opening up a window into its interior, offering us glimpses of what lies beneath. And there's something almost philosophical about transform faults, isn't there? They're boundaries that don't create or destroy, only accommodate motion. They're transitions that enable the larger system to function. Without transform faults, the rigid plates couldn't move the way they do. They'd run into geometric problems, unable to spread at ridges and subduct at trenches without these connecting elements. Transform faults are the solution to a geometric puzzle, the joints that allow a spherical planet's surface to rearrange itself while remaining continuous. So the next time you think of California or hear about an earthquake along the San Andreas Fault, remember, it's not a flaw in the Earth, not a mistake or weakness. It's a necessary feature, a transform boundary accommodating the motion of two great plates. It's been there for millions of years, quietly accumulating stress and periodically releasing it, and it will be there for millions more, long after human cities have crumbled and been rebuilt countless times. There's something comforting in that permanence, that indifference to human timescales. The Earth continues its slow dance, unconcerned with our brief existence, and we're privileged to witness one small moment of it. Now let's turn our gaze upward, toward the mountains. Those magnificent features that rise kilometers above sea level, their peaks scraping the sky, their slopes challenging climbers and inspiring poets. Mountains seem eternal, immovable, ancient beyond reckoning. And in human terms, they are. But from the perspective of plate tectonics, mountains are young, dynamic features, constantly being built up by tectonic forces and worn down by erosion, caught in an endless cycle of creation and destruction. Let's explore how mountains form, slowly, gently, one grain at a time. The process of mountain building is called orogeny, from the Greek words oros, mountain, and genesis, creation. There are several ways mountains can form, but the most dramatic examples are associated with convergent plate boundaries, where plates collide and crust is compressed, folded, faulted, and thrust upward. The most impressive mountain ranges on Earth, the Himalayas, the Andes, the Alps, are all products of plate convergence, monuments to the power of tectonic forces acting over millions of years. Let's start with the Himalayas, the tallest mountain range on Earth, home to Mount Everest and 13 other peaks over 8,000 meters high. The Himalayas are the result of a collision between two continental plates, the Indian plate and the Eurasian plate. This collision began about 50 million years ago and continues today, making the Himalayas one of the youngest major mountain ranges on Earth. But to understand how we got here, we need to go back further in time, to when India was not attached to Asia, but was a separate landmass far to the south. About 140 million years ago, India was part of the southern supercontinent Gondwana, nestled against Africa, Antarctica, and Australia. Then Gondwana began to break apart. India separated and started drifting northward, carried on a piece of oceanic lithosphere. As it moved, the ocean between India and Asia, called the Tethys Ocean, gradually closed. India travelled remarkably fast for a tectonic plate, moving up to 20 centimeters per year at times, much faster than typical plate velocities. It crossed thousands of kilometers, a continent adrift on the asthenosphere, heading inexorably toward a collision with Asia. About 50 million years ago, India collided with Asia. The oceanic lithosphere between them had been subducted, and now two continents met. But remember, continental crust is too buoyant to subduct. It's made of light, felsic rocks, granite and similar materials that resist being pulled down into the mantle. So when India and Asia collided, neither could subduct beneath the other. Instead, the crust crumpled, folded, and thickened, Sediments that had accumulated on the floor of the Tethys Ocean were scraped off and thrust upward. The edges of both continents were compressed and deformed. And slowly, grain by grain, the Himalayas began to rise. This process continues today. India is still pushing northward into Asia at about 5 centimeters per year. The crust in the collision zone is incredibly thick, up to 70 kilometers in some places, more than twice the normal thickness of continental crust. This thick crust is buoyant, causing the land to rise. But the story isn't as simple as just thickening crust. The collision has had far-reaching effects. Much of Tibet, a vast plateau north of the Himalayas, has been uplifted to an average elevation of over 4,500 meters. Faults slice through the region, accommodating the ongoing compression. Earthquakes are frequent, sometimes devastating, and the mountains continue to rise, even as erosion works to wear them down. It's remarkable to think about. Mount Everest, the tallest peak on Earth at 8,149 meters, is still growing. It gains a few millimeters in height each year as the tectonic forces pushing it up slightly exceed the erosional forces wearing it down. One day, perhaps millions of years in the future, these forces will balance or reverse and Everest will start to shrink. But for now, it grows, imperceptibly, patiently, adding grain to grain, crystal to crystal, in the slow work of orogeny. The Himalayas also provide a wonderful example of how mountains affect climate. The high peaks create a barrier to airflow, causing moist air from the south to rise and cool, dropping its moisture as heavy rains and snow on the southern slopes. This makes the southern Himalayas and the Indian subcontinent very wet, feeding rivers like the Ganges and Brahmaputra. Meanwhile, the northern side in Tibet is much drier, shielded from moisture by the mountains themselves. This rain shadow effect is common in mountain ranges and demonstrates how tectonics and climate are intimately connected. Now let's consider a different type of mountain building, exemplified by the Andes in South America. The Andes are the longest continental mountain range in the world, stretching over 7,000 kilometers along the western edge of South America. Unlike the Himalayas, which formed from a continent-continent collision, the Andes formed from a convergent boundary where an oceanic plate, the Nazca Plate, subducts beneath a continental plate, the South American Plate. This is called an Andean-type orogeny, and it produces a different style of mountain range. As the Nazca Plate subducts beneath South America, several things happen. First, the compression caused by the collision causes the continental crust to shorten and thicken, similar to what happens in a continent-continent collision, but to a lesser degree. Second, magma generated above the subducting slab rises through the continental crust and erupts, building volcanoes. Many of the highest peaks in the Andes are active or dormant volcanoes, their slopes composed of layers of lava and ash accumulated over millions of years. Third, blocks of crust are uplifted along faults, contributing to the overall elevation of the range. The result is a mountain range that's not just the product of crustal thickening, but also of volcanism and faulting, a complex combination of processes, all driven by plate convergence. The Andes are younger than the Himalayas in some sections, but the process of their formation has been ongoing for tens of millions of years. Like the Himalayas, they continue to rise, continue to be shaped by the slow, patient work of tectonics, even as erosion carved valleys and weathering breaks down rocks into soil and sediment. There's a third way mountains can form, though these tend to be smaller and less dramatic than those formed at convergent boundaries. Mid-ocean ridges, as we've discussed, are underwater mountain ranges, rising kilometers above the abyssal plains. When a mid-ocean ridge is particularly active, or when it intersects with a mantle hotspot, the mountains can rise above sea level, forming volcanic islands. Iceland is the most prominent example, an island sitting astride the mid-Atlantic ridge, built entirely by volcanic activity associated with both the ridge and an underlying mantle plume. Iceland is quite literally being pulled apart, with the eastern half on the Eurasian plate and the western half on the North American plate, and new crust forming in between. Mountains can also form through other, less tectonic processes. Volcanic hotspots can build mountains even in the middle of plates, far from any boundary. The Hawaiian Islands are an example, a chain of volcanic islands built as the Pacific Plate moves over a stationary mantle plume. Each island is a mountain rising from the ocean floor, built layer by layer as lava erupts and solidifies. The Big Island of Hawaii is currently over the hotspot and has active volcanoes. The islands to the northwest are progressively older, having been carried away from the hotspot by plate motion. Eventually, they'll be carried so far from the hotspot that volcanic activity will cease and erosion will gradually wear them down, transforming them from tall islands to low atolls and eventually submerged seamounts. But let's return to the collision-type mountains, because they embody so much of what's fascinating about orogeny. When you look at a mountain range like the Alps or the Appalachians, you're not just seeing high peaks, you're seeing the deformed remnants of ancient ocean basins, continental margins, volcanic arcs, entire geological provinces compressed, folded, and thrust upward. Sedimentary rocks that formed horizontally on an ocean floor now stand vertically on a mountainside. Rocks from deep in the crust have been brought to the surface. Fossils of marine organisms can be found at elevations of thousands of meters, silent testimony to the fact that what is now mountain was once sea floor. This brings up an interesting point about the age of mountains. While the rocks that make up a mountain range might be hundreds of millions or even billions of years old, the mountain range itself might be much younger. The Appalachian Mountains, for instance, formed during several orogenies, mountain building events, between about 480 and 300 million years ago. The rocks are even older in many cases. Precambrian rocks over 1 billion years old crop out in the Appalachian core. But the mountains themselves, as a topographic feature, are ancient. They've been eroded significantly since their formation. Once as tall as the Himalayas are today, they've been worn down over hundreds of millions of years to their current, more subdued elevations. This erosion is a crucial part of the mountain story. Even as tectonics pushes mountains up, erosion works to tear them down. Water, ice, wind, and gravity are relentless forces, breaking rock into fragments, transporting those fragments downhill, gradually leveling the land. In many cases, the battle between uplift and erosion reaches an equilibrium. The mountains rise, just as fast as they erode, maintaining a relatively constant elevation. But eventually, if the tectonic forces cease, erosion wins. The mountains are worn away, their material carried to the ocean to be deposited as sediment, which might one day be uplifted in a new orogeny, completing the cycle. So when you look at mountains, you're seeing a snapshot in time. The Himalayas are young, still rising, still sharp-peaked and rugged. The Appalachians are old, worn down, their peaks rounded by hundreds of millions of years of erosion. But both are products of the same fundamental process: plates colliding, crust thickening and deforming, land rising. It's a cycle that's played out countless times in Earth's history and will continue as long as plate tectonics operates. Mountains rise and fall. Ocean basins open and close. The surface of the Earth is constantly being rearranged, reshaped, renewed. And we, lying here contemplating these processes, are part of that story. Temporary inhabitants of a planet that's always in motion, always changing, always becoming something new. Breathe deeply. Let that wonder settle over you gently. Let's talk about earthquakes. Those sudden, sometimes terrifying moments when the ground beneath our feet moves, reminding us that the Earth is not the stable platform we imagine it to be. Earthquakes are manifestations of plate tectonics, the inevitable result of plates grinding past, colliding with, or pulling away from each other. They're releases of stress, sudden slips along faults, seismic waves propagating through rock. And while they can be destructive, even devastating, they're also fascinating geological phenomena, worthy of our attention and understanding. From the safety of your bed, let's explore them gently, without fear, as natural consequences of living on a dynamic planet. An earthquake begins with stress. Plates are constantly trying to move relative to each other, driven by forces in the mantle and by the geometry of the plate system itself. But the plates aren't free to slide smoothly. They're locked together along their boundaries by friction, by irregularities in the rock, by the sheer weight of the overlying crust. As the plates continue to push or pull, stress accumulates in the rocks along the boundary. The rocks deform elastically. They bend and stretch like a spring being compressed or extended. This can continue for years, decades, even centuries, with stress slowly building up, energy being stored in the deformed rock. Eventually, the stress exceeds the strength of the rock. The fault ruptures. The two sides slip suddenly past each other, releasing the stored elastic energy. This sudden motion generates seismic waves, vibrations that propagate outward through the earth in all directions, like ripples spreading out from a stone thrown into a pond. When these seismic waves reach the surface, the ground shakes. Buildings sway or collapse. The landscape can be permanently altered. And then, after seconds or minutes, it's over. The fault has slipped, the stress has been released, and the cycle begins again. The point within the Earth where the rupture initiates is called the hypercenter, or focus. The point on the Earth's surface directly above the hypercenter is called the epicenter. Shallow earthquakes with hypercenters less than 70 kilometers deep tend to be the most damaging because the seismic waves don't have to travel far to reach the surface. Deep earthquakes, occurring as deep as 700 kilometers in subducting slabs, are less dangerous because the seismic waves lose much of their energy traveling through the mantle before reaching the surface. Seismic waves come in several types. Body waves travel through the interior of the Earth. There are two kinds: P waves, primary waves, and S waves, secondary waves. P waves are compressional waves, like sound waves, where particles move back and forth in the direction the wave is traveling. They're the fastest seismic waves and the first to arrive at a seismometer. S waves are shear waves, where particles move perpendicular to the direction the wave travels. They're slower than P waves and can't travel through liquids, which is how we know that Earth's outer core is liquid. S waves don't pass through it. Surface waves travel along the Earth's surface, like ripples on water. They're slower than body waves, but often cause more damage because they have larger amplitudes and last longer. There are two main types: love waves, which cause horizontal shearing of the ground, and Rayleigh waves, which create a rolling motion like ocean waves. If you've ever felt an earthquake, the initial sharp jolt was probably the P wave arriving, followed by the stronger shaking of the S wave, followed by the rolling sensation of surface waves. It's a progression, a layered experience of different wave types reaching you in sequence. The magnitude of an earthquake is a measure of the energy released. The most commonly used scale is the moment magnitude scale, which has replaced the older Richter scale. The moment magnitude is calculated based on the seismic moment, a value that takes into account the size of the fault rupture, how much it slipped, and the rigidity of the rocks involved. The scale is logarithmic, meaning that each whole number increase represents a tenfold increase in amplitude of seismic waves and about 31 times more energy released. A magnitude 7 earthquake releases about 31 times more energy than a magnitude 6, and about 1,000 times more than a magnitude 5. Small earthquakes are incredibly common. Worldwide, there are millions of earthquakes each year, though most are so small that they're only detected by sensitive instruments. Earthquakes below magnitude 3 are rarely felt by people. Above magnitude 3, they might be felt by people near the epicenter. Magnitude 5 earthquakes can cause minor damage. Magnitude 6 can cause significant damage in populated areas. Magnitude 7 and above are major earthquakes that can cause widespread destruction. The largest earthquake ever recorded was the 1960 Valdivia earthquake in Chile with a magnitude of 9.5. It ruptured a fault over 1,000 kilometers long and killed thousands of people. The intensity of an earthquake describes the effects at a particular location and is different from magnitude. The modified Mercalli intensity scale ranges from I, not felt, to TUS, total destruction. A single earthquake has one magnitude, but many different intensities depending on how far you are from the epicenter, the local geology, and the type of structures present. Near the epicenter, intensity might be X or Xing, catastrophic damage. Farther away, it might be V or VI, moderate shaking, some damage. Even farther, perhaps 2 or 3, weak shaking, felt by few. The intensity decreases with distance, but not uniformly. Local geological conditions can amplify or dampen the shaking. One of the most important factors affecting earthquake damage is the local geology. Areas with soft sediments, especially water-saturated sediments, experience much stronger shaking than areas built on solid bedrock. This is because the soft sediments amplify seismic waves. Worse still, saturated sediments can undergo liquefaction during strong shaking. The soil temporarily loses its strength and behaves like a liquid. Buildings sink, tilt, or collapse. Underground pipes break. The ground can open up in fissures. It's one of the most destructive effects of earthquakes, turning solid ground into something that flows and heaves. Earthquakes can also trigger other hazards. Landslides are common in mountainous areas, where earthquake shaking can cause unstable slopes to fail. Avalanches can be triggered in snowy regions. And of course, there are tsunamis, giant waves generated when an earthquake displaces a large volume of water. Megathrust earthquakes at subduction zones are particularly prone to generating tsunamis because they involve large areas of the seafloor suddenly moving vertically, displacing the overlying water. The 2004 Indian Ocean tsunami, triggered by a magnitude 9.1 earthquake, killed over 230,000 people in 14 countries. Waves over 30 meters high struck coastlines hours after the earthquake, demonstrating the far-reaching effects of seismic events. Yet for all their destructive potential, earthquakes are a natural and necessary part of plate tectonics. Without earthquakes, stress would build up indefinitely, with no mechanism for release. Earthquakes are how the Earth accommodates plate motion on a planet where the lithosphere is rigid and brittle. They're inevitable consequences of living on a tectonic planet. And interestingly, most plate boundary regions have adapted to them. In Japan, California, Chile, and other earthquake-prone areas, building codes are strict, early warning systems are in place, and people are educated about earthquake safety. The goal isn't to prevent earthquakes, that's impossible, but to mitigate their effects, to live with them as a fact of geological life. Scientists study earthquakes to better understand plate tectonics and to improve our ability to assess seismic hazards. Seismometers around the world detect and record seismic waves from earthquakes, allowing researchers to determine the location, depth, and magnitude of events within minutes. Networks of GPS stations measure subtle ground deformation, showing how stress is accumulating along faults. Paleoseismic studies examine the geologic record of past earthquakes, looking for evidence of ancient ruptures in trenches dug across faults. All this information helps build a picture of earthquake frequency, magnitude, and recurrence intervals. Crucial data for assessing risk and planning for future events. Can we predict earthquakes? This is one of the most frequently asked questions in seismology, and the answer is both disappointing and hopeful. We cannot predict earthquakes in the short term. We can't say that a particular fault will rupture on a particular day. The processes involved are too complex, too chaotic, with too many variables influencing whether and when a fault will slip. However, we can make long-term forecasts. We can identify which faults are likely to rupture in the coming decades or centuries. We can estimate the magnitude of earthquakes they might produce. And we can map areas at risk, allowing for better planning and preparedness. It's not prediction, but it's useful information nonetheless. One area of active research is earthquake early warning systems. These systems use the fact that seismic waves travel at finite speeds. When an earthquake occurs, seismometers near the epicenter detect it within seconds. They can send out an alert that travels at the speed of light, far faster than the damaging seismic waves. This gives people farther from the epicenter a few seconds to tens of seconds of warning before strong shaking arrives. It's not much time, but it's enough to take cover, to stop surgeries, to halt trains, to shut down industrial processes. Japan and Mexico have sophisticated early warning systems. California has implemented one as well. They don't prevent damage, but they can reduce it, and they save lives. There's something oddly comforting about understanding earthquakes, isn't there? They're not random acts of an angry planet. They're not punishments or omens. They're natural phenomena, predictable in their general behavior, even if not in their exact timing. They're the Earth's way of accommodating the slow, inexorable motion of plates. And while they can be destructive, they're also reminders that we live on a dynamic planet, a world that's alive in its own geological way, constantly changing and adjusting. From a safe distance, from the warmth of your bed, earthquakes lose some of their terror and become fascinating subjects of contemplation, windows into the deep processes that shape our world. Breathe. The Earth moves, and that's okay. Now let's turn to volcanoes, those dramatic features where Earth's internal heat breaks through to the surface, where molten rock erupts in displays of fire and ash, where new land is created even as old landscapes are buried. Volcanoes have captivated and terrified humans throughout history, seen as both destructive forces and manifestations of the divine. But from the perspective of plate tectonics, they're simply places where magma reaches the surface, driven by processes deep within the Earth. Let's explore them gently, appreciating their beauty and power from a comfortable, safe distance. Magma is molten rock beneath the Earth's surface. Once it erupts and flows out onto the surface, we call it lava. The difference is just one of location. Below ground, it's magma. Above ground, it's lava. But the generation of magma is a complex process, intimately tied to plate tectonics. Remember that although the mantle is mostly solid, it can melt under certain conditions. The three main ways to melt mantle rock are increasing temperature, decreasing pressure, and adding water or other volatiles that lower the melting point. All three mechanisms are at work at different plate boundaries, creating magma that feeds volcanoes. At mid-ocean ridges, decompression melting occurs. As plates pull apart, the underlying mantle rises to fill the gap. As it rises, the pressure on it decreases, and when you decrease pressure on hot rock, its melting point drops. Even though the rock doesn't get any hotter, it starts to melt because the lower pressure allows melting to occur. This partial melting generates basaltic magma that rises to create new oceanic crust. The process is continuous, slow, and remarkably consistent. It's been happening for billions of years, creating ocean floor grain by grain, eruption by eruption. At subduction zones, the mechanism is different. Here, water released from the descending slab lowers the melting point of the mantle wedge above it. This is called flux melting. The addition of water acts as a flux, promoting melting even though the temperature might not be particularly high. The resulting magma is more silica-rich than mid-ocean ridge magma, creating andesitic or dacitic magma that tends to erupt explosively. These subduction zone volcanoes form volcanic arcs, chains of volcanoes parallel to the trench, either on land, like the Andes, or as island arcs, like Japan or the Aleutians. The third setting for volcanism is hotspots, places where mantle plumes rise from deep in the earth, possibly from the core mantle boundary. These plumes are thought to be narrow columns of hot mantle rock, ascending through the surrounding cooler mantle. When a plume reaches the base of the lithosphere, the hot material undergoes decompression melting, generating basaltic magma that can erupt at the surface. Because hotspots are stationary relative to the moving plates above them, they create chains of volcanoes as the plate moves over the hotspot. The Hawaiian Islands are the classic example. a chain of islands and seamounts formed as the Pacific Plate has moved northwestward over the Hawaiian hotspot for the past 80 million years. Volcanoes come in different shapes and sizes, depending on the type of lava they erupt and the style of eruption. Shield volcanoes, like those in Hawaii, have gentle slopes and broad bases. They're built from fluid basaltic lava that flows easily, spreading out over large areas before solidifying. Each eruption adds a thin layer to the volcano, and over thousands of eruptions, a massive mountain builds up. Mauna Loa in Hawaii is the largest volcano on Earth by volume, though measured from its base on the ocean floor rather than from sea level. It's a gentle giant, its slopes so gradual you could walk up them without feeling like you're climbing a mountain. Yet it rises over 9,000 meters from the seafloor to its summit, taller than Mount Everest. Stratovolcanoes, also called composite volcanoes, are much steeper. These are the classic cone-shaped mountains we think of when we imagine a volcano. Mount Fuji, Mount Rainier, Mount Vesuvius. They're built from alternating layers of lava flows and explosive volcanic deposits, ash, pumice, volcanic bombs. The magma that feeds stratovolcanoes is more viscous, more gas-rich, and tends to erupt explosively. These eruptions can be catastrophic, sending ash and pyroclastic flows down the mountainside, burying valleys and towns. Yet between eruptions, they can be peaceful for decades or centuries, covered in vegetation, looking more like ordinary mountains than sleeping dragons. There are also smaller volcanic features. Cinder cones are small, steep-sided cones built from volcanic cinders and ash ejected from a single vent. They typically form in a single eruptive episode and don't grow very large. Volcanic fields can have dozens or hundreds of cinder cones scattered across a landscape. And then there are calderas, massive depressions formed when a volcano collapses into the void left by a massive eruption that emptied the magma chamber beneath. Yellowstone, Crater Lake, and many other famous volcanic features are calderas, testament to eruptions so enormous that they changed the landscape and climate of entire regions. Volcanic eruptions can be incredibly varied in style and intensity. Effusive eruptions, where lava flows out relatively gently, are typical of basaltic volcanism at mid-ocean ridges and hotspots. The lava flows down the flanks of the volcano, solidifying into smooth or ropey textures, creating new land. Explosive eruptions, on the other hand, fragment the magma into ash and pyroclastic material that's blasted into the atmosphere. The 1980 eruption of Mount St. Helens in Washington state was explosive, removing the entire north face of the mountain and sending ash across the northwestern United States. The 1815 eruption of Mount Tambora in Indonesia was even more powerful, ejecting so much ash into the atmosphere that it caused global cooling, creating what's known as the Year Without a Summer in 1816. One of the most dangerous volcanic phenomena is a pyroclastic flow, a fast-moving current of hot gas, ash and rock fragments that flows down the slopes of a volcano during an explosive eruption. These flows can reach speeds over 700 kilometers per hour and temperatures of 1,000 degrees Celsius. They incinerate everything in their path. The city of Pompeii was buried by pyroclastic flows from Mount Vesuvius in 79 AD, preserving the city and its inhabitants in volcanic ash for nearly 2,000 years. It's a stark reminder of volcanic power, but also a fascinating archaeological time capsule. Yet for all their destructive potential, volcanoes are also creators. They build new land, adding to islands and continents. The Hawaiian Islands didn't exist until volcanism created them. Iceland is still growing as volcanic eruptions add new land. Volcanic soils, once they weather, are incredibly fertile, supporting lush vegetation and productive agriculture. Some of the most densely populated areas on Earth are near volcanoes: the slopes of Mount Vesuvius, the Indonesian islands, the Rift Valley of East Africa, because the soil is so rich. People have learned to live with the risk, drawn by the benefits volcanic landscapes provide. Volcanoes also play a crucial role in Earth's climate and atmosphere over geological timescales. Volcanic eruptions release gases, water vapor, carbon dioxide, sulfur dioxide, and others into the atmosphere. Over billions of years, volcanic outgassing has contributed significantly to the composition of our atmosphere and oceans. On shorter timescales, large eruptions can inject enough sulfur dioxide into the stratosphere to reflect sunlight and cool the planet for a few years. The Pinatubo eruption in 1991 cooled global temperatures by about 0.5 degrees Celsius. It's a reminder that Earth's surface and atmosphere are interconnected systems, with volcanic activity linking the deep interior to the air we breathe. Scientists monitor active volcanoes using a variety of techniques. Seismometers detect the small earthquakes that often precede eruptions as magma moves beneath the surface. GPS and tilt meters measure subtle changes in the volcano's shape as magma accumulates in chambers below. Gas sensors measure emissions from volcanic vents, looking for changes that might signal rising magma. Satellite imagery tracks thermal anomalies and surface deformation. All this monitoring helps volcanologists assess volcanic hazards and issue warnings when eruptions seem imminent. While we can't prevent eruptions, we can often predict them hours to days in advance, allowing evacuations that save lives. There's something deeply primal about volcanoes, isn't there? They're windows into Earth's interior, places where the planet's heat and energy manifest at the surface. They remind us that beneath the thin, cool crust we inhabit, the Earth is hot, molten, still cooling from its formation billions of years ago. Volcanoes are part of that cooling process, releasing heat, allowing the planet to gradually shed the energy it was born with and the energy generated by radioactive decay in its interior. They're necessary, inevitable features of a tectonic planet. And while they can be destructive, they're also beautiful, powerful reminders of the dynamic world we live on. From a distance, from the safety of your bed, you can appreciate them without fear, marveling at the fire that builds mountains and creates land. Sleep well, knowing that Earth's fires burn slowly, patiently, usually far from where you rest. Now, let's step back from individual mountains and volcanoes and look at the bigger picture. The grand choreography of continents moving across Earth's surface over hundreds of millions of years. This isn't just random wandering. There's a pattern, a cycle, where continents periodically come together to form supercontinents, then break apart and drift across the globe, only to reassemble millions of years later in a different configuration. It's called the supercontinent cycle, and it's one of the most majestic processes in all of geology. Settle in. Let's watch the continents dance across deep time. The most recent supercontinent was Pangaea, which we've already mentioned. Pangaea existed from about 335 to 175 million years ago, assembling during a period of mountain building called the Variscan orogeny, and persisting through much of the Permian, Triassic, and early Jurassic periods. At its maximum extent, Pangaea included almost all of Earth's continental crust, assembled into one massive landmass, surrounded by a single global ocean called Panthalassa. It was a world utterly different from today. Different climates, different ocean circulation patterns, different distributions of life. Imagine standing on the shores of Pangaea, looking out over an ocean that stretched for thousands of kilometers in every direction, knowing that all the land on Earth lay behind you, peaceful, vast, primordial. But Pangaea wasn't the first supercontinent, and it won't be the last. Before Pangaea, there was Pannotia, which existed around 600 million years ago. Before that, Rodinia, around 1 billion years ago. Before that, Columbia, around 1.8 billion years ago. And possibly others even earlier, though the evidence becomes increasingly uncertain as we peer deeper into geological time. Each of these supercontinents assembled, persisted for perhaps 100 to 200 million years, then broke apart, with the fragments drifting across the globe before eventually reassembling into a new configuration. It's a cycle with a period of roughly 400 to 600 million years, the supercontinent cycle. Why do continents periodically come together? The mechanisms aren't entirely clear, and geologists are still debating the details, but the basic idea is this. When a supercontinent forms, it blocks the flow of heat from the mantle beneath it. Heat accumulates under the supercontinent, eventually creating mantle upwellings, hot plumes of material rising from below. These plumes thin the lithosphere, create rifts, and initiate the breakup of the supercontinent. As the fragments drift apart, the ocean basin between them grows. But this spreading can't continue indefinitely. Eventually, the ocean basin reaches its maximum size and starts to close as subduction zones develop around its margins. The fragments, having traveled across the globe, eventually collide again, forming a new supercontinent in a different configuration. And the cycle begins anew. Let's trace the cycle starting with Pangaea, since that's the one we know most about. Pangaea began to break apart about 200 million years ago. The first rift formed between what would become North America and Africa, creating the Atlantic Ocean. Over tens of millions of years, this rift widened. South America split from Africa. India separated from Antarctica and began its rapid journey northward. Australia broke away from Antarctica. The continents that had been joined in Pangaea were now scattered across the globe, separated by growing ocean basins. The breakup of Pangaea didn't happen all at once or uniformly. Some rifts succeeded, opening into full ocean basins. Others failed, leaving behind rift valleys filled with sediments. The East African Rift, for example, might be a nascent ocean basin, a place where Africa is slowly splitting apart. In a few tens of millions of years, the rift might widen into a new ocean, separating the African continent into two pieces. Or it might fail, leaving behind a rift valley that gradually fills with sediment and becomes dormant. The future is uncertain, unwritten, still being decided by the slow interplay of tectonic forces. Today, we're in the middle of the dispersed phase of the supercontinent cycle. The continents are scattered across the globe, far from being assembled into a supercontinent. But the process is already beginning to reverse. The Atlantic Ocean is still spreading, but the Pacific is shrinking as subduction zones around its margins consume ocean crust faster than it's being created at mid-ocean ridges. Eventually, perhaps 200 to 300 million years from now, the continents will collide again, forming a new supercontinent. Geologists have proposed several scenarios for how the next supercontinent might form. One scenario, called Novo Pangaea, envisions the Atlantic continuing to spread while the Pacific closes completely. The Americas would collide with Asia, Antarctica would drift northward and collide with Australia and Asia, and Africa would continue its northward journey into Europe. The resulting supercontinent would form roughly where the Pacific Ocean is today, with a new ocean basin occupying the space where the Atlantic currently lies. Another scenario, Pangaea Ultima, imagines the Atlantic beginning to close, perhaps within the next 50 million years, as new subduction zones form around its margins. The Americas would move eastward, eventually colliding with Africa and Europe. Antarctica would drift northward. The result would be a supercontinent roughly centered on the current Atlantic, with the Pacific still a vast ocean on the other side of the planet. This scenario is favored by some geologists because old ocean basins tend to close eventually as new subduction zones form around their margins. A third scenario, Orica, envisions both the Atlantic and Pacific closing while new ocean basins open elsewhere. This is the most complex scenario, involving the formation of new rifts and ocean basins that don't currently exist. The continents would assemble into a supercontinent roughly centered on the current Indian Ocean, with new oceans on either side. It's the least predictable scenario, requiring changes in plate motions and boundaries that we can't confidently forecast. Which scenario will actually occur? We don't know. Predicting hundreds of millions of years into the future is inherently uncertain. New rifts might form in unexpected places. Subduction zones might initiate or cease. Mantle convection patterns might change. All we can say with confidence is that plate tectonics will continue, continents will move, and eventually, barring some catastrophic change to Earth's interior, a new supercontinent will form. It's inevitable, written in the patterns of Earth's past, likely to unfold in its future. But the details remain mysterious, hidden in the deep time that stretches ahead of us. The supercontinent cycle has profound effects on Earth's climate and life. When continents are dispersed, as they are today, ocean circulation can distribute heat more effectively around the globe, moderating climate extremes. Continental interiors are relatively small, so most land is near coasts, benefiting from maritime climates. But when a supercontinent forms, conditions change dramatically. The interior of a supercontinent, thousands of kilometers from any ocean, experiences extreme continental climate, scorching summers, freezing winters, low rainfall. Deserts can dominate vast regions. The lack of oceanic barriers allows species to migrate freely across the supercontinent, increasing competition and possibly driving extinctions. Ocean circulation also changes. With continents blocking major ocean currents, heat distribution becomes less efficient. This can lead to greater temperature differences between the equator and poles, potentially triggering ice ages or extreme warming. Some scientists think that the assembly of supercontinents might trigger mass extinctions as climates change and habitats are disrupted. Certainly, major extinction events in Earth's history often coincide with times of significant tectonic reorganization. The end Permian extinction, the largest mass extinction in Earth's history, occurred during the existence of Pangaea, possibly related to climate changes driven by the supercontinent configuration. When supercontinents break apart, the opposite occurs. New ocean basins form, creating new habitats. Continents drift apart, isolating populations and allowing evolution to proceed independently on each landmass. This increases biodiversity as species diversify in isolation. The breakup of Pangaea, for instance, is thought to have contributed to the diversification of mammals and flowering plants in the Mesozoic and Cenozoic eras. Australia, isolated from other landmasses for tens of millions of years, developed its unique fauna, marsupials and monotremes that evolved nowhere else. South America, also isolated for much of the Cenozoic, developed its own distinctive mammal groups. When continents reconnect, as they inevitably do, there's a mixing of faunas, sometimes called the Great American Interchange, when North and South America connected a few million years ago. New species arrive, old species go extinct, and ecosystems are transformed. It's all part of the rhythm of the supercontinent cycle. There's something humbling about the supercontinent cycle, isn't there? The continents we know, with their familiar shapes and positions, are just temporary configurations in an endless dance. The map of Earth has never been static. It's always been in flux, always changing, and it always will be, as long as plate tectonics continues. 200 million years ago, the world was unrecognizable. 200 million years from now, it will be unrecognizable again. We live in one brief moment of this endless cycle, fortunate enough to be conscious of it, able to reconstruct the past and speculate about the future. Take a breath. Let the vastness of geological time wash over you. The continents drift, the dance continues, and we're here, now, a fleeting witness to one turn in an ancient waltz. Now let's consider a question that might seem obvious, but is actually quite profound. Why does Earth have plate tectonics? It seems like such a fundamental feature of our planet that we might assume all rocky planets must have it. But as far as we know, Earth is the only planet in our solar system, and possibly the only planet anywhere, with active plate tectonics. This uniqueness is not accidental. It's the result of specific conditions that exist on Earth and apparently nowhere else. Understanding what makes Earth special helps us appreciate just how remarkable our dynamic planet really is. Let's start by looking at our neighbors in the solar system. Venus is nearly Earth's twin in size and mass, and it presumably has a hot interior similar to Earth's. Yet Venus has no plate tectonics. Its surface is a single unbroken shell of lithosphere covering the entire planet. There are no mid-ocean ridges creating new crust, no subduction zones consuming it, no transform faults accommodating lateral motion. The surface of Venus is old, perhaps 500 million years on average, suggesting that the entire surface was resurfaced in a global volcanic event at that time. Since then, there's been little tectonic activity. Why Venus lacks plate tectonics is a mystery, though it might be related to its extremely hot surface temperature, over 450 degrees Celsius, and lack of water, both of which we'll discuss in a moment. Mars is smaller than Earth, with only about half Earth's diameter and a tenth of its mass. It too has no plate tectonics. Mars did have extensive volcanic activity in the past, building enormous shield volcanoes like Olympus Mons, the largest volcano in the solar system. It also has a massive canyon system, Valles Marineris, that dwarfs Earth's Grand Canyon. But these features aren't products of plate tectonics. They're products of mantle plumes and crustal rifting in a single-plate lithosphere. Mars's surface is ancient, heavily cratered, showing that it hasn't been resurfaced by tectonic activity for billions of years. The planet has cooled, its interior is mostly solid, and whatever tectonic activity it might once have had has long since ceased. Mercury and the Moon are even smaller and have been geologically dead for eons. Their surfaces are cold, rigid, and covered in impact craters dating back billions of years. Neither ever had plate tectonics. They're one-plate planets, their lithospheres solid and immobile. The outer planets, Jupiter, Saturn, Uranus, Neptune, are gas and ice giants with no solid surfaces, so plate tectonics is not relevant to them. Their moons, however, are interesting. Some, like Europa and Enceladus, have icy shells that might undergo a form of plate tectonics, with ice sheets moving and subducting in a cold analogue of Earth's system. But that's speculation, and even if true, it would be fundamentally different from rocky planet tectonics. So what does Earth have that allows plate tectonics to operate? Several factors seem to be important. First, Earth is the right size. It's large enough to have retained significant internal heat over billions of years, driving mantle convection. But it's not so large that the lithosphere is too thick and rigid to break into plates. There's a Goldilocks zone for planetary size and plate tectonics, and Earth happens to fall within it. Too small, like Mars, and the planet cools quickly, solidifying completely. Too large, like a super-Earth several times Earth's mass, and the lithosphere might be too thick for plates to form or subduct. Second, Earth has water, lots of it. Water plays multiple crucial roles in plate tectonics. It lowers the melting point of mantle rock, facilitating magma generation at subduction zones and mid-ocean ridges. It lubricates faults, making it easier for plates to slide past each other. It hydrates minerals in the oceanic crust, which then release water as they subduct, triggering volcanism. And water at the surface weathers rocks, creating sediments that are swept into trenches and contribute to the subduction process. Without water, plate tectonics might not be possible, or at least, would operate very differently. Venus, with its extremely hot surface, has no liquid water. Mars has some water ice, but very little liquid water and only a thin atmosphere. Earth's abundant water might be the secret ingredient that makes plate tectonics work. Third, Earth's crust is compositionally divided into continental and oceanic types, with different densities. This density difference is crucial for subduction. Oceanic crust is dense enough to sink into the mantle when it's old and cold. Continental crust is too buoyant to subduct. This asymmetry drives the plate tectonic system, with oceanic plates recycling into the mantle, while continental plates remain at the surface, accumulating over billions of years. Venus might not have this compositional differentiation, which could be another reason it lacks plate tectonics. Fourth, Earth's lithosphere is the right thickness and strength to form discrete plates that can move independently. The boundary between the lithosphere and the underlying asthenosphere is well defined, allowing the rigid plates to glide on the weaker asthenosphere beneath. This might seem like a minor detail, but it's essential. If the lithosphere were too weak, it would deform continuously rather than breaking into discrete plates. If it were too strong, it would be too rigid to break at all. Earth's lithosphere is just right, brittle enough to fracture into plates, but strong enough that those plates are coherent and can move as units. And finally, Earth's mantle convection is vigorous enough to drive plate motions, but not so vigorous that it would disrupt the plates entirely. The balance between the strength of the lithosphere and the forces driving it is delicate. Too little mantle convection, and plates wouldn't move. Too much, and the lithosphere might be overwhelmed, unable to maintain discrete plates. Earth sits in a sweet spot where mantle convection provides just enough force to keep the plates moving without destroying the plate tectonic system itself. All of these factors, the right size, abundant water, compositional layering, appropriate lithospheric strength, and balanced mantle convection, came together on Earth in a combination that apparently didn't occur on other planets in our solar system. This makes Earth unique, at least among the worlds we've been able to study. And it might make Earth rare even among rocky planets throughout the galaxy. We don't know for certain. We haven't studied enough exoplanets to say whether plate tectonics is common or vanishingly rare. But the fact that none of our neighboring planets have it suggests it's not the norm. This uniqueness has profound implications for life. Plate tectonics regulates Earth's climate over geological time by recycling carbon between the surface and the interior. Carbon dioxide, released by volcanoes, is removed from the atmosphere by weathering and carried into the mantle by subducting plates. This carbon cycle helps maintain temperatures within a range suitable for liquid water and life. Without plate tectonics, carbon dioxide might accumulate in the atmosphere, like on Venus, resulting in a runaway greenhouse effect, or be lost to space, like on Mars, resulting in a cold, dry planet. Earth's plate tectonics might be one of the reasons Earth has remained habitable for billions of years. Plate tectonics also creates diverse habitats. Mountains, valleys, ocean basins, volcanic islands, rift valleys, all are products of tectonics and all support different ecosystems. The constant rearrangement of continents isolates populations, driving speciation and increasing biodiversity. Some scientists argue that complex life might not have evolved without plate tectonics providing this environmental diversity and driving evolutionary innovation. It's speculative, but intriguing. Perhaps intelligence, civilization, and all of human history are indirect consequences of plate tectonics, of living on a restless planet that never settles into stasis. There's something both humbling and comforting about Earth's uniqueness. We live on a dynamic planet, one that has maintained conditions suitable for life for over 4 billion years through a complex interplay of geological processes. We're the beneficiaries of circumstances that might be rare in the universe, and we're part of an ongoing story, living through one moment in Earth's long geological history. The plates will continue to move long after we're gone, reshaping the planet, creating new worlds for future life forms, if any exist, to inhabit. We're temporary, but the dance is eternal. Rest in that thought. It's soothing in its way. We've journeyed through Earth's past and present, understanding how plate tectonics works and how it has shaped our planet over billions of years. Now let's gaze forward into the future, contemplating what might lie ahead for Earth's dynamic crust. Of course, predicting the distant future is uncertain, perhaps impossible in detail, but we can make educated guesses based on current plate motions, our understanding of the supercontinent cycle, and the physics of planetary cooling. Let's explore the possibilities, gently, without anxiety, knowing that whatever happens will unfold over timescales so vast that they dwarf all of human existence. In the short term, say the next few million years, we can predict plate motions with reasonable confidence. Current velocities and directions suggest that Africa will continue moving northward, gradually closing the Mediterranean Sea. Eventually, perhaps in 50 million years, Africa might collide with Europe, creating new mountain ranges to rival the Alps. The Atlantic will continue spreading, pushing the Americas farther from Europe and Africa. The Pacific will continue shrinking as subduction zones around its margins consume oceanic crust. Australia will drift northward, eventually colliding with Southeast Asia. These are straightforward extrapolations of current plate motions, barring any unexpected changes in mantle convection or the formation of new plate boundaries. Looking farther ahead, as we discussed in the supercontinent cycle section, the continents will eventually reassemble into a new supercontinent, perhaps 200 to 300 million years from now. Whether this will be Nova Pangaea, Pangaea Ultima, Orica, or some other configuration, we can't say with certainty. But the cycle is likely to continue, driven by the same forces that have operated for billions of years. The new supercontinent will persist for perhaps 100 to 200 million years before breaking apart again, scattering continents across the globe in a new configuration. And so the cycle will continue, again and again, as long as Earth's interior remains hot enough to drive mantle convection and plate motions. But here's the crucial question. How long will plate tectonics continue? Forever? Or will Earth eventually cool enough that plate tectonics ceases, leaving us with a static one-plate planet like Venus or Mars? The answer depends on how Earth's interior evolves over the coming billions of years. Earth's internal heat comes from two sources: residual heat from the planet's formation and heat generated by radioactive decay of elements like uranium, thorium, and potassium in the mantle and crust. Both of these heat sources are diminishing. The primordial heat is gradually radiating into space. The radioactive elements are decaying into stable isotopes, producing less heat over time. Eventually, billions of years from now, Earth's interior will cool enough that mantle convection slows or stops, and plate tectonics will cease. Current estimates suggest that Earth has enough internal heat to drive plate tectonics for at least another billion years, possibly much longer. Some models suggest plate tectonics might continue for 2 or 3 billion years. Others think it could persist even longer, perhaps until the Sun becomes a red giant and swallows Earth in about 5 billion years. The uncertainty reflects our incomplete understanding of Earth's interior and the complex feedback mechanisms that regulate heat loss. But the general consensus is that we have at least 1 billion years of plate tectonics ahead of us, a timescale so vast that it's almost meaningless in human terms. Civilizations will rise and fall, species will evolve and go extinct, and through it all, the plates will continue their slow dance, reshaping the world again and again. When plate tectonics does finally cease, what will happen to Earth? The planet won't become completely geologically dead immediately. There might still be some volcanic activity, driven by localized hotspots or residual heat. But the major features of plate tectonics, mid-ocean ridges, subduction zones, the movement of continents, will gradually wind down. The continents, wherever they happen to be at the time, will freeze in place. No more mountain building through continental collision. No more ocean basins opening and closing. The surface will become static, gradually worn down by erosion into a flatter, less dramatic landscape. It's a melancholy thought in a way, the end of Earth's geological dynamism. But it's also deeply in the future, so far ahead that it barely seems real. There are other changes ahead too, unrelated to plate tectonics, but worth mentioning. The Sun is gradually getting brighter as it ages. In about 1 billion years, the Sun will be about 10% brighter than it is today. This increased solar output will drive Earth's climate into a runaway greenhouse state, evaporating the oceans and making the planet uninhabitable for complex life. By the time plate tectonics ceases, Earth might already be a sterile, Venus-like world. In 5 billion years, the Sun will expand into a red giant, its outer layers extending possibly beyond Earth's orbit. The Earth might be engulfed and destroyed, or it might survive as a scorched, airless rock orbiting the white dwarf remnant of the Sun. Either way, the Earth as we know it will be gone. But let's not dwell on the ultimate end. That's billions of years away, an almost incomprehensible span of time. For now, for the foreseeable future, Earth will remain a vibrant, dynamic world. Plate tectonics will continue shaping the surface, creating mountains and ocean basins, driving volcanism and earthquakes, regulating the climate, and supporting the incredible diversity of life that makes our planet so special. We're living in Earth's prime, in the long middle age of a planet that will remain active and habitable for hundreds of millions, even billions of years to come. That's a comforting thought, isn't it? We're not witnessing the twilight of a dying world, but a vibrant, ongoing story, one chapter in an epic that's billions of years long and still unfolding. So as you drift towards sleep, think about the journey we've taken. From Earth's layered interior to its dynamic surface, from the discovery of continental drift to the modern understanding of plate tectonics, from divergent boundaries creating new crust to convergent boundaries recycling it, from transform faults accommodating lateral motion to the slow dance of the supercontinent cycle. We've explored mountains rising, earthquakes shaking, volcanoes erupting. We've contemplated Earth's uniqueness among planets and speculated about its long future. Through it all, one theme emerges. Earth is not static. It's dynamic, constantly changing, perpetually reshaping itself. And we, fleeting as we are privileged to live on this restless world, to understand its processes, and to marvel at its beauty. The plates will continue to drift long after we're gone, carrying the continents on their slow journey across the globe, writing the next chapters of Earth's geological story. Rest easy in that continuity. Sleep well. How do continents move? It's the question that brought us here, whispered softly at the beginning like a child asking if the ground beneath their feet has always been where it is now. And after wandering through Earth's layered interior, across mid-ocean ridges spreading slowly, down subduction zones where old crust returns to the mantle, along transform faults where plates slide and grind, up mountain ranges still rising grain by grain, through the shaking of earthquakes and the fire of volcanoes. Across the supercontinent cycle from Pangaea past to Pangaea future, we find ourselves gently circling back to where we began, still wondering, still fascinated by the dynamic planet we call home. We've learned that Earth is not a solid, static ball, but a layered, dynamic system where heat from deep within drives the motion of rigid plates across a plastic mantle. We've explored how Alfred Wegener noticed patterns that others overlooked, proposing continental drift decades before the evidence proved him right. We've discovered the three types of plate boundaries: divergent, convergent, and transform, and seen how each creates its own characteristic geological features. We've descended into subduction zones where oceanic crust sinks back into the mantle. We've risen with mountain ranges built by colliding continents. We've felt the ground shake with earthquakes and watched volcanoes release the mantle's heat. We've traveled through time, watching Pangaea assemble, break apart, and imagining how continents might one day reunite in a new supercontinent billions of years hence. And we've understood that plate tectonics makes Earth unique in our solar system, a world alive with geological activity, constantly reshaping itself, never the same twice. Maybe the movement of continents doesn't have a simple, singular explanation. Maybe it's driven by mantle convection, by the weight of subducting slabs, by ridge push and slab pull and forces we haven't yet imagined. Maybe the exact mechanism is less important than the observable fact that it happens, that the ground beneath us is part of a grand slow dance that's been ongoing for billions of years and will continue for billions more. Maybe that's the whole point, not to pin down every detail, but to stand in awe of the process itself, to feel wonder at the thought that the apparently solid Earth is actually fluid over deep time, that nothing is permanent, that the world is always in the process of becoming something else. Maybe that wonder, that sense of connection to processes larger and older than ourselves, is the most valuable thing we can take from this journey. So, with all of this in mind, are you still awake? If you are, I hope it's not because I was too interesting, though the story of plate tectonics is fascinating enough to keep anyone captivated. If I did manage to hold your attention through all these words about moving continents and convecting mantle, well, at least you've learned something remarkable about the planet you live on, about the ground you rest upon each night. And if you're already halfway to sleep, drifting peacefully on the edge of dreams, then I've succeeded in what I set out to do. Either way, you've been a wonderful companion on this gentle journey through geological time. Before you drift off completely, I'd love to know where you're listening from and what time it is in your part of the world. Drop a comment and share. Are you perched on the edge of a subduction zone, where one plate slowly descends beneath another? Or perhaps you're resting near a mid-ocean ridge, above a place where new seafloor is being born even as you sleep. Tell me which tectonic plate you call home and whether plate tectonics feels more real to you now, or if the ground still seems reassuringly solid and still. I'd love to hear your thoughts. If you found this gentle journey into plate tectonics relaxing or informative, or both, please do consider giving this video a like and subscribing to Sleepy Science Student. It's a small gesture that helps me keep bringing you more calming, curious content from the world of earth science and beyond. Your support means the world to me, or perhaps I should say, it means the world and all its slowly drifting continents to me. Thank you for joining me on this journey through the dynamic crust of Earth. Sleep well, dream deep, and may your rest be as patient and peaceful as the movement of tectonic plates, as enduring as ancient continents, as gentle as magma slowly cooling beneath the sea. Know that the ground beneath you is part of a story billions of years in the making, and you are resting on a page in that endless book. All you have to do is close your eyes and become part of that ancient, ongoing narrative. Good night.